Welcome to the lecture on connection in composite structure. The connection in composite structure are very similar to bare steel connections. In composite connection, in addition to the bare steel connection behavior, there is a additional strength is derived from the reinforced slab, which is placed at the top of the flange of a beam or top of any flange of the steel member. So there are some design factors to be considered for the composite connections. The first factor is ultimate moment rotation behavior and ultimate strength of the connection, plastic rotation capacity of the joint and plastic requirement, that is to have a proper mechanism. What will be the requirement is required to have a plastic hinges, especially in the intermediate structures. The following are the assumptions made in the beam column connection. The very first assumption is steel under compression is also found to be uniform and to the maximum yield stress, and the area of concrete in tension zone is eliminated, and the strain hardened region of reinforcing steel is eliminated, and the resistance to transfer of shear is solely by the steel part, and the reduction in the moment capacity due to the presence of shear is neglected. These are the factors you have to consider while doing the connection design. Before going for composite connection, we'll see some of the simple connections as well as the common connections. Simple connection means this is a pictorial representation of simple connection. This is the example of fin type connection. Fin plate will be there, a beam web to be brought closer to the fin plate and bolts to be placed. Either bolt or weld to be made to connect the fin plate to the beam web. So here this is a pure shear connection. That means usually the connection behavior are represented as a moment rotation behavior. That is, what is the force here? Moment from the beam to the column is transferred through the connection. So the force on the connection is said to be a moment, and for the given moment, because of ductility present in the fin plate, it undergo a relative rotation with respect to the column. So therefore, the behavior of the column is said to be m theta behavior. If it is a pin connection, it will not take any moment, but it undergo large rotation. So therefore, such cases, such connections are said to be pin connections. The next connection is a rigid connection, or otherwise it is said to be a continuous connection. Their moment is expected to transfer completely. Here, if the connections are made by attaching more element to connect a beam to the column, then such connections are said to be rigid connections or continuous connection, where in a very ideal condition, the connection will transmit all the moment from the beam to the column. But this is very ideal. In no connection will behave like this. Here, because of the ductility present in the connecting element, say here a header plate, extended plate is used to connect the beam to the column, and some bolts, some bracing plates are included to increase the rigidity of the connection. Therefore, here from the graph, it is ideal behavior of a fixed connection, that is complete moment is transferred from beam to the column. So such connections are said to be rigid connections. So the actual common behavior is none of the connection will show a behavior parallel to this direction or to this resistance direction. It is in between. Such connections are said to be semi-rigid connection. That means the connection will behave neither pinned manner nor rigid manner. It is in between. There are some conventional type of steel connection which are popularly used in composite construction. Coming to the force present in the composite connection, see here, this is a welded connection, this is a bolted connection. In both the case, this is nothing but a concrete slab, this is a reinforcing steel, and here the beam is connected to some group of bolts with a plate. Here directly it is welded with a seating element. So I'll explain the behavior of connection by this diagram. Here, this is the force taken expected to taken by the reinforcing steel and group of bolts. Here, what happened? The under the bending of beam, this bolt group is subject to a tension compression system. Some of the bolt may be suppose under the application of moment, it will the neutral axis will fall here, suppose for a case. In that case, some of the bolts are in compression, some of them are in tension. In addition to the reinforcing steel contention, the total system subject to a tension compression system. So that will resist the applied moment. So while doing any composite design, the following steps should be followed. First, we have to determine the reinforcing steel capacity at the connection end. Then, if the decking sheet is provided along the length of the beam, then that tension capacity of the decking sheet also to be taken, which is equal to Fm. Then we'll see to it the forces in the bolts, especially in the tension zone, by assuming a suitable neutral axis. Then drawing the free body diagram, and we can for example, if this is the tension system, then we'll draw the stress block, and you can identify the region where the connection going to subjected to compression. Based upon that, you locate the neutral axis and you do suitable arrangement for the bolt forces. Necessary assumption has to be made. Then finally you calculate the moment capacity, because you know what are the forces under tension side and what are the things are in compression side. So this equal and opposite force with the lever arm will create a moment of resistance. So to calculate the moment of resistance, you have to identify the location of a neutral axis. There are four possible cases to assume the neutral axis. The very first assumption is the neutral axis will be within the concrete slab. The next one is within the upper portion of the flange of the beam. The third case is which is above this the bolt group region. Next one is with the few bolt group either or within this bolt group region. This is the possible way to assume the neutral axis. This is one real trial. You have to do one or more trial to identify the actual neutral axis. This is the another issues in the composite connection, where under the tension compression system, under the compression, this web of the column will undergo three major problem or risks. One is when this web may undergo buckling due to excessive compression, local shear. This compression will create a shear in the web, and here the bearing problem will be happen, because at this region the web as well as the flanges interaction region may subjected to a bearing failure. Due to the bearing failure, the web may undergo crippling. So all the things you have to properly taken care by providing suitable measure. So the best measure will be, you can go for say say this form of stiffness. Say either you can provide stiffness along the length of the flanges of the beam, as well as you go for a diagonal bracing. So this stiffness will avoid the failure, the three modes of failure of the web of your column web. Okay, so how to avoid remedy? As I said that you can go for web plate, double plate or diagonal stiffness, or otherwise you provide a bearing stiffness to the web of the column flange. Thank you. This is all about your connections in the composite construction. Thank you very much.